In this video, I want to talk about the grid point singularity table that you find in the F06 file when working with MSC Nastran. Now, this is the first take of this video, so things might be a little unorganized. But hopefully by the end of this table, you have a better understanding of what this table means. Now, I'm going to be using the MSC Nastran Linear Static Analysis User's Guide. If you refer to this section, Automatic Application of Single Point Constraints, you have this expression, Ri equals Ki over K max. If you look at this table, you can see a few columns in this table. One of the columns is the stiffness ratio. This value, Ri equals Ki over K max, this is the stiffness ratio. So let me go ahead and do this. Let me go ahead and take a screenshot of this. And let me copy it here because we're going to be talking about this a lot today. So this is the stiffness ratio expression. We're going to talk about how do we get this value. And as an example, we're going to consider this finite element model. It's basically a collection of beam elements. It's fixed on the free end on the left, and then we have a load applied at the right end. When I run this, and if I look in the F06 file, I do get a grid point singularity table. I also get a warning or a fatal message, user fatal message 9050. This is related in this case to the grid point singularity table, so we'll go ahead and talk about this more now. So the first thing I want to cover, where does this value come from? Why this value? So now let me do this. So let's suppose we have a node, and then I'll call this n, and then this node here, this is n prime. So this is the deformed position of the node. So you can see that if this was the x component and this was the y component, you can see that the x component of this node is governed by stiffness. And then the y component of this node is governed by another stiffness that I'm representing with these springs. So I'll call this maybe K1 here and K2 here. So what the stiffness ratio is doing is the following. Let's suppose my K1 is equal to 1E10 Newton meters. So you can see it's very, very big. It's a very stiff spring. But then suppose K2 is maybe a very soft spring, maybe 0.001 Newton meter. Suppose this was a very soft spring. And then consider this as part of a larger set of nodes. So here at the bottom we have another spring. It has its own springs. It has its own spring values. These other springs are on the order of 10 to the power of 10. So here 10, 10. So here, if all these springs are on the order of 10, but then this spring is very small, the spring value is very small rather, the stiffness ratio helps us identify those so-called soft springs. So in this example, what we do is we calculate the stiffness ratio for the one direction, which would be this direction, and then the two direction would be in this direction. And then we look at the stiffness ratios. If the stiffness ratios are very small, that's a problem. So if they're small, this could be an indication of very soft springs, relatively soft springs. And this might indicate an issue relatively soft. So again, stiffness ratio is a measure of relatively how soft the spring is. If it's very small, if you have a very small stiffness ratio, then the spring is very soft. And this is possibly bad. So now, how do we calculate this value? So if you look at this value, they actually tell us how they calculate it. They say take the ith term on the K matrix and divide it by the principal stiffness. So now, how do we find the ith term in the K matrix, and how do we find the stiffness matrix? So to do this, let's go ahead and take that bulk data file. So we'll go ahead and take it and paste it here. And let's go ahead and add a command to output the stiffness matrix. So here what I'm going to do is take this command and paste it here. Oh, it's already here. And I'm going to run it in Nastran. So let's go ahead and run it with Nastran real quick. When you run it with Nastran, you get this new H5 file. So this is what the name of the H5 file looks like. What I'm going to do is open that H5 file here. Now the tool I'm using today is HDF-View. This tool is actually free to download and use. If you go to the website HDF-View, I think it's called HDF Group actually. If you sign up for their website, you get to download this tool for free. Here, if you look at the left-hand side, there's a matrix KAA. If you open that, that gives you the stiffness matrix for the example we'll be working with today. Now, let's go ahead and take a look at this. So this is node 1, and we've constrained all 6 degrees of freedom here. For node 2, all the degrees of freedom are unsupported. So if you look back at this matrix, this is what we have. So here we have column 0, column 1, column 2, column 3, 4, so on and so on. These first 6 columns, if you will, these are going to be the first degree of freedom, the second, the third, the fourth, the 5th, and the 6th degree of freedom for node 2. And then the next columns, 7, 8, so on and so on, this is going to be the 1st, 2nd, 3rd, 4th, and so on and so on for node 3. And now let me look at one information here. We're going to do this for the rotation degrees of freedom. Okay, so if you look here, let me take a screenshot of this. So suppose that we want to find the stiffness ratio for this value here. So this is going to be K, well here in this case it's K33 because the index starts with 0. Here if you want to think about it, this is also K44 if the index started with 1. Here let me just take a step back. I'll call this K33 for now. So how do you find the stiffness ratio? First you find the element, which we did. And let me make sure this is aligned to the notes that I have. Okay, so maybe we'll have to do this a little differently. Okay. Oh, degree of freedom 6. Okay, I'm reading this a little incorrectly. Okay, so this is what we're going to do. Not this one. Let me take a step back here. So what we want to do is do it for this value, sorry. So this is going to be K55. So if you look at the document, they tell you how to find the principal stress. And here I'm not. That's okay. I'll just tell you how we find it. So what we do is we take those, we take a 3x3 cut of the stiffness matrix. So here we're taking a cut for just the rotations, and we find the eigenvalues for this matrix. So this is a 3x3, and we find the eigenvalues. So here, what I've already done before, if I've used Python, right, so here let's go ahead and do this. Let's move this side by side. So if you look here, this term is here on the right in my Python window here on the right. This next diagonal is 7.68. This is also here on the right. And then I'm using NumPy to find the eigenvalues. And if I run it, here are my eigenvalues. So that would be this diagonal matrix. No, it would be this right here. That would be my eigenvectors. Okay, so this array here are my eigenvalues. So now which value is the principal stiffness? It'd be the largest eigenvalue here, which would be this value. So I think in the book they had a K max equals this. And then my K55 is equal to, what do we have it before? I think it was 9.02. So let's go ahead and do that. Let's copy this value. And then I don't know if it's going to let me. Let's go ahead and copy it here. So then the stiffness ratio, and remember that's going to be K55 over K max. It's going to be equal to this. So let's go ahead and do this division here. I'm just going to do the division here in the web browser. Let's go ahead and copy paste that. And then I get 1.44. And if we look at the F06 file, let's go ahead and look at the singularity table. So right now we determine the stiffness ratio for node 2 for degree of freedom 6. So if I go back here, let me go ahead and explain this again. So this is node 2, degree of freedom 1, 2, and 3. So these are the translation degrees of freedom. And then we have 4, 5, and 6, which are the rotation degrees of freedom. So we wanted to know the stiffness ratio for the 6th degree of freedom, which would be this column. So we use this value here, which is K55. And then we found the principal stiffness by finding the maximum eigenvalue for this 3x3 matrix. So we went ahead and did the arithmetic, and we got this value. So then here, let me go ahead and do this, equals this, 1.44. Now, if I look at the singularity table, we get the same value. So let me copy and paste that here. So if you look at this column tells you the node ID or the grid ID. So here I see that this row is the stiffness ratio for node 2. And this point happens to be a grid point. There's another type of point called a scalar point. But here the G is telling us that this is a grid point, not a scalar point. So G is the grid ID 2, degree of freedom 6. The stiffness ratio is 1.14. Now if we wanted to, we could do this for another value. Here we could do it for node 3, degree of freedom 2. So if we wanted to, what we could do here, so then here would be degree of freedom 1, 2, and 3. This would be node 2. And then here, let's go ahead and see where we're at. So this would be degree of freedom 1 and then degree of freedom 2. So this would be K77. K77. And then what we need to do is we need to cut out a 3x3 matrix. So notice that this is only for translations. The 3x3 is only for the translation degrees of freedom. And then here, let's go ahead and see how simple it is to calculate it. 2e. Okay, perfect. So you'll notice one thing about this matrix. This matrix it only has diagonal terms. It's 2, 2, and then 1.93. And actually, I think this one's 2e negative 11. The next one is 2e negative 35. And then the other one is, let's go ahead and see, negative 13. So now, what are the eigenvalues of this matrix? Since all the non-diagonal terms are zeros, these are the eigenvalues essentially. So what's the maximum eigenvalue? It's going to be 2e negative 11. So now, I think which one? Let me go back to this table. Right, okay. Fell direction 3 and 2. Okay, so let's do this. So let's start writing some data here. So K77 is equal to, remember, we want to do this for this row. So this is telling us node 3. Did I annotate this right? Right. So these first 6 degrees of freedom, this is node 2. Then the next 6 degrees of freedom, this is node 3. So it's very important. And then here in the singularity table, we want to do this for direction 2. So then when we do direction 2, this is going to be degree of freedom 1, degree of freedom 2. So that would be this term here. So what we did, we went into the stiffness matrix and we got that value. The value is actually this value here. So 2e negative 35. This is K77 divided by the principal stiffness, which is the max eigenvalue, which is 2e negative 11. This should get us the following value. So let's do that real quick. 2e negative 35 divided by 2e negative 11. One e negative 24. So let's go ahead and make sure. Okay, perfect. Yep. So this is aligning. So here, when we did this arithmetic, we get 1e negative 24 here on the right. And then when we look back at the singularity table, we also get that value here. So we get 1.0e negative 24. So hopefully this explains how we calculate the stiffness ratio. And now let's talk about how we use this information to diagnose the issue. So now, if we look at our beam model, this is node 1, this is node 2, this is our x, our y, then our z is out of here. So we have a T1, T2, and then T3. So these are going to be our translation degrees of freedom. And then we're going to have our rotation R1, R2, and then R3. These are going to be our rotation degrees of freedom. A lot of the time you see these referred to as the 1, the 2, the 3 translation degrees of freedom, the 4, the 5, and the 6 degrees of freedom. Now, let's take a step back from here. And let's look at what's going on here. If we look at this table, we're being told that the stiffness ratio for grid 2 is very small for the rotation degree of freedom. So now we have to ask ourselves, why is this happening? So if you look at node 2, this is our node 2 here. Maybe let me use red. This is node 2. So you could think that there is a torsional spring, if you will. So let me go ahead and write the degrees of freedom. So this is degree of freedom 1, 2, and 3. You can imagine that there is a stiffness term in the stiffness matrix. So if we go back here, this 2, or let me go back to degree of freedom 2, or node 2. So let's talk about this part of the stiffness matrix. Wow, it's getting very complicated very quickly. So let me do this. So remember, the first 6 degrees of freedom are for node 2. And then for the next 6 degrees of freedom, they're node 3. So this is going to be our translation degrees of freedom and then our rotation degrees of freedom. Now remember, we calculated the stiffness ratio for this term. The stiffness ratio is very small. That's a problem for us. Now we have to ask ourselves, why is the stiffness ratio very, very small? If you go back to this diagram, the torsional stiffness for degree of freedom 6 might look something like this. So let's go ahead and draw that torsional stiffness. So maybe it looks something like that. And then there's a torsional stiffness for degree of freedom 1. And then degree of freedom 2. So now, remember back to one of the earlier slides. If the surrounding stiffnesses are high, so 10 to the 10 as an example, but then one stiffness is very small, then the stiffness ratio for that degree of freedom would be very, very small. So here I'm being told that the following. I'm being told that the stiffness ratio for degree of freedom 3 is very, very small. So what does that mean? That means that the stiffness, the torsional stiffness for the other axes are very large. So you can imagine there's a very big stiffness for degree of freedom 1, and then degree of freedom 2. And then for degree of freedom 3, there's a very small torsional stiffness here. So in rotation about the z-axis, the stiffness is very, very small. So your K3, which in the global stiffness matrix is K55. It's very, very small. So what's going on here? So we're dealing with beam elements. So this adds stiffness to the following degrees of freedom. So here, so translation, it adds stiffness. For rotations, it adds stiffness. So here, these are checkboxes saying that it adds stiffness to those degrees of freedom. And then for the other node, it's the same thing. So we have stiffness for the translation and for the rotations. But this is telling me one problem here. For some reason, this node has a very small stiffness for rotation along the 6th degree of freedom. Now, you should be careful with other elements, because other elements, they're a little different. So here, let's go ahead and take a look at a C-hexa element. If you look at 1 degree of freedom, or 1 node rather, sorry, and then we have our degrees of freedom. So we have translation. So here, this element does supply stiffness along the translation degrees of freedom, but for the rotations, it adds no stiffness. There's zeros. So if we go back to the beams, the beam is adding rotational stiffness for the 6 degree of freedom, but there's something a little weird or off about that degree of freedom. So if we look in Patron, let's go ahead and try and find what's going on here. Now, let me make this comment about a beam. The stiffness for the degrees of freedom, it's going to be a function of a few things. It's going to be a function of the Young's modulus, the shear modulus, I think it's called G, and it's going to be a function of the area, the moment of inertias, and then I think there might be a few others I don't know about, but I'll say that. So now we have to inspect all of these. What is supplying rotational stiffness here? What could it be? So if we look back at the bulk data file for 2, let's look at mat 1. Okay, so the Young's modulus is 100, the Poisson ratio is 0.3, the density is 1000. But now what's going on with the cross section? We're using a bar cross section, so let's go ahead and take a look at the cross section here. Let's go ahead and look at this and calculate the display. And then when we look at the display, it's going to look a little weird. This is a rectangular cross section with a dimension or a width of 0.1 and a height of 1e negative 12. You notice that the height, it's 1e negative 12. So this is what this beam looks like. So the beam has a width of 0.1. So here it's 0.1, but then the height of this beam is very, very small. So it's very, very small. This is the height, so it's 1e negative 12. So this is a problem for us. You can see that the moment of inertia about this axis, it's reasonable. But then the moment of inertia across this axis, it's very, very small. So now that we know this, let's go back to the beam example. What's going on with the beam? So if our beam, and here what I'm going to do is something like this. This is the X, this is the Y, and this is the Z. So our beam looks like this. It's fixed on this end, and then there's a force here. So here, we know that our beams have a width of 0.1. So this is the width of 0.1, but our height is very, very small. So now for this beam element also, this is the width of the cross section, but then the height's very, very small. Same thing here. The height's very small. So this is the beam is wide, which is okay, but the beam is very, very short. Now this is bad because this is going to add a very small rotational stiffness. So now that we've identified what's causing the small stiffness, we can go back into Patron and we can fix this. We can say, oh, I made a typo. It should actually be 0.1. Let's go ahead and apply this. Oh, looks like I might have to... Oh, here, let's go ahead and use the modify option. Now let's go ahead and run this again. Let's go ahead and see what my output is now. So if we go back to the beam. Okay, perfect. So one, the singularity table is no longer here, and now we actually get some solutions. We get some displacements and some forces. So we fixed this. So let me sum up what we did here. So for each node, you have a spring for the first degree of freedom. You have a spring for the second degree of freedom, and here I'm overlapping the springs. And then if this was X and this is Y, then this is Z. And then for this direction, we get another spring. So this is degree of freedom 3. Now the stiffness ratio, this is equal to K, well, they call it Ki over K max. So K max, this is going to be the principal stiffness. Remember, this is the max eigenvalue for the 3x3 matrix. Now you do this for the translations and rotations separately. So then we do this for each node, for each degree of freedom. And basically what we're doing, we're comparing the springs. We're comparing the springs to find out if there's one spring that's really, really soft or 0. If there's a spring that's really, really soft or 0, that's a problem. We have to identify what's contributing to the very small spring value. And let me give you another example. Let's suppose we have a cube like we do in this example here. So basically, I've fixed the base and I apply a load to the top. And now, what does the stiffness matrix for this look like? So let me go ahead and do this. Let me go ahead and run this. And let's go ahead and look at this file here. What I'm going to do is I'm going to turn off AUTOSPC param. AUTOSPC equals no. And then let's go ahead and run that example. And let's look at the F06 file. Okay, now when we run this example with AUTOSPC off, we have this grid point singularity table. And we have a big problem here. Let's go ahead and talk about what's going on here. So let me take a screenshot of this, paste it here. And let me do this. Let's go ahead and see what the stiffness matrix for this example looks like. So I'm going to add this command, I'm going to run it. And then let's go ahead and open the stiffness matrix in this other program. So this first 3x3 matrix, this is the stiffness for the first translation degrees of freedom. But then if you look at the next terms, and then here what I'll do is I'll take a screenshot of this. So these first 3 columns, these are for translation, trans, and then the next 3 degrees of freedom, these are rotations. And then the next ones are trans, and then the next 3 are rotations, and so on and so on. Now you'll notice that these columns are all zeros. So this is bad, because when you try to find k-1, which is going to be equal to the adjoint of k, and let me create a new page, or let me do this. How do I do this? Let me do this at the bottom. So when you try and find the inverse one way to find the inverse is to do the adjoint of k over the determinant of k. With these 0 columns, you'll notice that the determinant of k is equal to 0. So then this creates an undefined solution of inverse of k. So now, one thing you can do is you can remove these degrees of freedom. You can set them aside. So how do you remove these degrees of freedom? So what you can do is this. Or actually, first let's answer why there's 0 for now. So each element type, so 0D, 1D, 2D, and 3D, each element type will add a different number of stiffnesses to each degree of freedom. So for 1D elements, generally all 6 degrees of freedom get a stiffness, a non-zero stiffness. So, and then for 2D, in most cases, it's 5 degrees of freedom that get stiffnesses. For 3 degrees of freedom, each node gets 3 degrees of freedom for the stiffnesses. Let me reword this. This is a little too wordy, so let me do this. So for one node, a beam will supply 6 Ki. For 2D, each node would get 5 stiffness values. For 3D, each node gets only 3 stiffness values. For the 3D case, we saw this in the stiffness matrix a moment ago. So here, for the translation degrees of freedom, we get this. For the rotation degrees of freedom, a 3D element does not supply stiffness for the rotation degrees of freedom, so they're all zeros. And then it varies from element to element. So for 1D as an example, we get stiffnesses for all 6 degrees of freedom. So again, remember the Young's modulus, the length of the beam, the cross-section area, the moment of inertia. These are all values that contribute to the degree stiffnesses rather. Same thing for the 2D element. There's going to be a Young's modulus, the shear modulus, the thickness of the shell. There are other parameters I can't remember off the top of my head, but I'm sure there are other parameters that contribute to the thickness, or the stiffness, sorry. For the 3D elements, the same thing. The Young's modulus, the shear modulus, I think. The width and the height, I guess, for the element. These are all things that contribute to the stiffness. And then for the 0D element, it gets a little bit complicated, but I'll leave that for another day. So now, if we go back here, we know that 3D elements don't supply rotational stiffness, so they're all zeros. What do we do here? What we can do is we can move these degrees of freedom to the side, and the way we can do that is the following. Here in Patran, what I'm going to do is I'm just going to add supports to those rotational degrees of freedom. So if I go here and I create a new support called turn off rotations, I'm going to just supply that the rotational degrees of freedom all have zeros. Click apply. We'll click analyze entire model. Click apply here. And then one thing I did here, let me turn off AUTOSPC. Now if I run this, if I look into the F06 file, I still have these terms. Let me go ahead and close this and open again. I still get these terms. Let's go ahead and see what's going on here. So AUTOSPC is turned off. It seems like that. What's happened here, I did create the support, but it wasn't added to the load case. So let's go ahead and add it here. Turn off rotations. Okay, so it's been added. Let's go ahead and double check the degrees of freedom that were turned off. So rotations. Oh, okay. The one thing I forgot to do, I forgot to select all the nodes. So let's go ahead and select all the nodes and click apply. And let's redo this. And let me turn off AUTOSPC. You might be asking, what is AUTOSPC? And I'll explain that in a moment. So let's go ahead and run Nastran again. If I look inside the F06 file, okay, there's something wrong here. Oh. There I had 0 where I was supposed to specify no text characters. So now if I run the F06 file again, now it runs. You notice that the singularity table is no longer there. Now, what does the stiffness matrix look like for this example? So what I'm going to do is rename this. Call this B maybe. Let's go ahead and add the command that supports the output of the stiffness matrix. Let's go ahead and run this bulk data file. And let's go ahead and open the stiffness matrices side by side. So you notice that the first element is the same value in both of these matrices, but you notice that for columns 3, 4, and 5, here on the right, columns 3, 4, and 5 are no longer 0 columns. That's because we've set aside the rotation of degrees of freedom when we set the support equal to 0 in Patran. So if you recall a few moments ago, what we went ahead and did in Patran was we did the following. We said that, okay, so I know that these 3D elements, they're not supplying any rotational stiffnesses to the nodes. That's okay. I'm going to say that those rotational degrees of freedom are all zeros. This effectively removes those from the stiffness matrix on the right. So now I can go ahead and perform the inverse and find a solution for this scenario. So if we look back at the singularity table for that example, I don't know if I'll get it. Maybe here in this document I had, perfect, here. So if we look back here at the very starting grid point singularity table here, all of these degrees of freedom were the rotational degrees of freedom 4, 5, and 6. It was telling me, hey, there's no stiffness for these rotational degrees of freedom. Do something. So here what we manually went ahead and did, we said that for the 4, 5, and 6 rotational degrees of freedom, say that the rotations for all of these degrees of freedom, they're all 0. So then this effectively removed all these columns that has zeros, and then once you remove that, for k -1, this was actually possible. So I did get a value for that. I was able to get a solution there. So here, let me now recap here. So suppose we have a 3D element here, and let's suppose that we attach a beam element here. So this is our beam element. So there's one beam element here and then a 3D element here. When you look at this node, if you look at K, and K has a lot of data, for the 1, 2, 3, 4, 5, and 6, you'll actually get non-zero terms here. I don't know, there'll be maybe 1 and 2. I'm just making these up. 3, 4, 5, and 6. So for this degree of freedom, you'll get non-zero terms for the translation and the rotation degrees of freedom. But for this other node, where it's only connected to the 3D element, so here we continue on the stiffness matrix, and here again it starts again. 1, 2, and 3 for the translation degrees of freedom, but then the other elements, they're all zeros for the rotations. So going back here, the stiffness ratio is very useful for identifying soft springs or springs that are zero. So here, nearly zero. Now, going back to AUTOSPC, what AUTOSPC does, let me close some of this. What AUTOSPC does, it looks at that original stiffness matrix it computes those stiffness ratios, and it says, okay, some of your degrees of freedom have very small stiffnesses, or the stiffnesses are zero. You know what? Those might be degrees of freedom that you manually want to SPC them. So if you look at this table, okay, let's do this. Let's go ahead and remove that boundary condition for the rotations, and now let's just go ahead and run this. Let's go ahead and open that 06 file. We still get the grid point singularity table, but you'll notice that it's a little different this time. So let me take a screenshot of this. So if you look at the old singularity table, you notice that this degree of freedom was part of the B set. So you look at all these, they were B's. And then after, it was still part of the B set. But after we use AUTOSPC, things look a little different. If you look carefully, before these degrees of freedom were part of the B set, but now these degrees of freedom are part of the SB set. So what's happened here is that internally, these degrees of freedom were free before. And if you remember a few moments ago, we manually constrained them. We added SPC, single point constraints, all equal to 0. So thetas were all equal to 0. So we manually did this before. When AUTOSPC is on, and by default it's on, it does the same action automatically. It automatically adds the SPCs for the degrees of freedom. So here S indicating, I believe it stands for SPC. And I think if we look in the reference guide, let's go ahead and see if we can find this table. What I want to look for in this document is set, because the section discussing set describes what all those degrees of freedom are. So let's go ahead and see if we can find it. Okay, here we go. So perfect. So B, let's go ahead and see if we can find B. So B is, so the B set can be thought of as kind of a free node, but look here with SB. Degrees of freedom eliminated by single point constraints that are in boundary condition changes and by AUTOSPC. So if we look back here, before, these degrees of freedom were free. They were in the B set. But then after, they were in the SBC set. So this would be the nodes that are constrained with SBCs. So we know that the 3D elements don't supply any rotational stiffness. So what we went ahead before is we manually added the SBCs. With AUTOSPC, it does this automatically. Now, it's very important that you be careful with this, because sometimes you might be tempted to do this. So maybe that's not a good example. I don't know. I'm making up this example, so it may or may not be right, but I think I want to use this example just to communicate my point. So suppose that you have this setup here, and you have a beam here. It's a very small beam. Some of the terms may be really, really small, so maybe 1e negative 8 as an example. I'm just exaggerating. If you're not careful, the stiffness ratio might be really small. So I think it's 1e negative 7 is the tolerance. If the stiffnesses or the stiffness ratios, if they're really small for this degree of freedom, I'll just go ahead and constrain it. So here I'm using a fixed support icon to communicate that it's being supported here. So this is a problem, because it might actually remove degrees of freedom that you want to. What might be a good example here? Right, so let me demonstrate this with a very simple scenario here. Suppose you have that beam just modeled like this, and then here is the hexahedral element, and we applied a force here, and then it's fixed here. Suppose for some reason the stiffness ratios here were very, very small. What might happen with AUTOSPC equals true, it will add another support here. It will eliminate those degrees of freedom, which is effectively like adding a support. It will add a support here, which is maybe something you don't want. So it's important to look at the grid point singularity table. If you have values in the grid point singularity table, it's important to ask yourself, okay, is this supposed to do this? This is not supposed to do this. So there you have it. That's a grid point singularity table. Again, this was the first take. I might do another take, maybe not. I'll do this. How about if you have a question, leave the question in the YouTube comments below. If I see that there's still a lot of confusion with this grid point singularity table, then maybe I'll do this take again. So hopefully I can better communicate what the grid point singularity table is. So let me quickly recap what we went over. This whole video was about the grid point singularity table. So there'll be this image here. What I wanted to do was to explain what the stiffness ratio is and how to interpret these different columns in the grid point singularity table. We basically saw that the grid point singularity table is a measure of the stiffnesses relative to each other. So here you can imagine there are stiffnesses for the 1, the 2, and the 3 degrees of freedom. If one stiffness was very, very soft relative to the other stiffnesses, this stiffness was reported in the grid point singularity table. We went ahead and discussed how to use this table to identify where there's a problem in the models we were working with. We also discussed the AUTOSPC feature. This sometimes removes degrees of freedom from K. and then we discussed some considerations regarding that. So again, this was the first take in the video, so it was a little unorganized. If you do have a question, leave it in the YouTube comments. If I see from the YouTube comments that there's still a lot of confusion with the grid point singularity table, then I'll redo this video later on in the future. So with that, I'll stop here, and as always, thank you so much for watching.